All right, now it gets a little harder, a little trickier. Actually, not harder, just a little trickier. You got to learn a few new rules. All right, we're going to do parallel circuits. Page 15, 16, 17, 18. It just keeps going. Really, it just goes to 18. So let's review a little bit and let's go over some stuff. So let's look at number 1. A circuit in which all charge flows in a single pathway. So we're keying on single. Is a blank circuit. A circuit in which charge flows in multiple pathways is a blank circuit. So single pathway equals series, just like this. As you guys know by now, multiple pathway equals parallel, which would be like this. All right, cool. That one's an easy one. All right, number 2. For a parallel circuit, as the number of resistors, so remember, we're talking about a parallel circuit this time. So if you remember from the last video when we went over a series, we kind of started a few questions. We're like, this is going to come up later. This is one of those questions. For a parallel circuit, as the number of resistors being used within the same parallel circuit increases, so we add more resistors, the overall resistance value decreases. Okay, so this is going to be decreases for this first one. And the overall current value, so the current will actually increase in a parallel. Sorry. Number 3, we talked about this in a little bit. Household currents are connected in parallel so that blank. All right, so household, in your house, the circuits are connected in parallel. What's the reason is what they're saying. A, houses get the same effect with less current and thus save on energy cost. The turning off of one appliance does not result in shutdown of others, and hazard electrocution, and overheating of circuits is avoided. This one is B. So you turn off one. You don't want to connect them like this, right? You turn off your toaster or whatever. You unplug your toaster and then or actually it'd probably be more like a light, and then your whole house shuts off. Yeah, you don't want to do that, right? All right. So let's look at number 4. We're going to read this and then we're going to go over some stuff and then we're going to do number 4. Actually, I'm not going to do this. I'm just going to kind of go over it. All right. When the water flow or charge flow is divided into 2 or more separate pathways, as in a parallel circuit, the sum of the current in each individual pathway, sum means add. By the way, I think it means add. It should mean add. The sum, I lost my spot. The sum of the current in each individual pathway equals the total current. Utilize the principle to fill in the blanks below. The meters in the diagram are measuring water flow rates in gallons per minute. In other words, when you're doing a parallel circuit and you're dealing with current, the current in each pathway level will equal the total current. So the one pathway level here will equal 100. This pathway will equal 100. This pathway will equal 100, and it should end with 100. Let's talk about this real quick, because I know that's huh? So remember when we talked about a series. In a series, when you want to find equivalent resistance or total resistance, you just add the individual resistance together, and that gives you total resistance, right? And in a series, we knew that the total current was equal to the current of the first unit, which is in the second unit. The current, in other words, the current never changes. The total current is always the same, no matter where you are in a series, right? In a parallel, the current rule is switched. The current rule is exactly like the resistance rule in series. In other words, the current changes depending on where you are in the circuit, and they all add up to be the total current. Unlike series, where the current's the same, and the resistance add up. In parallel, the current adds up. So let's come back over here. So looking at this, the current in was 14. This is a parallel, so the current in each of these will add up to be 14. 6 plus 5 is 11, 12, 13, 14. And then the current out again is 14, right? So if you need help on this, ask me. I'll do one with you guys. So I'll do a couple of sides with this one. So we know that the current in, or this is gallons per minute of water, but the concept is the same, is 100. So when it divides into this row, 40 is on one side, so it should equal 100, so this should be 60, right? As we go to the next one, we're dealing with these three parts. 1, 2, 3. This one is what? It's 40, right? This whole pipe is 40, which means we have this, and again, it should equal 100. And then as you go to the bottom, there you go. This side's a little more challenging. Starts at 100, divides into 3 pipes, you bring it down. Now it divides into 1, 2, 3, 4 pipes. 1, 2, 3, 4, yeah. And then it comes down to 1, really just 1, but like one long one, and you can add them together or whatever. So try to do this on your own. You can look up the answers. I think it's on the website where you get your info, but I think it's kind of fun, to be honest, so I wouldn't look them up. Ooh, I folded it a little short. All right, so let's finish this page. Apply the same principle to fill in the blanks in the following diagram for charge flow. Current through a parallel circuit. So remember we said the current total is the sum of each individual current. So again, if the current total is 12, current in a parallel circuit, then it's going to be 6 plus 2 is 7, 8. And this has to be 4 for the current total to be 12. Remember, current is I, right? And it's the deal is amps. So this one, the total current is 6. And each individual one is 2. Plus 2 is 4, which means whatever's left has to equal 6. So that's going to be 2. So there you go. So to sum up this page, the rule for resistance, calculating resistance as a series, is kind of like an equivalent rule for current in a parallel circuit. Electricity, it's so electrifying. Yeah. Okay, so let's do this page. This is probably one of the more challenging pages just because it's like you got a little bit of math, you got a little bit of remembering stuff. It's a little tricky. So sit tight. I'm going to pause. I'm going to collect some notes, and then we're going to rock and roll. Okay. I hope you're amped up. I hope your current has flown through the roof because it's about to get real. All right. So let's look at number 6. So hopefully you remember what we just went through. The total current, which is amps, right, equals the sum of each individual current shift. So in other words, we talked about this. The current of these individual pieces, when the current will actually drop, will equal the total, unlike in series where it's always the same. So that being said, the total current is 12, which means it should drop an equivalent of 12. So 5 plus 4 is 9. What's left over? 3. So that's our current here. So let's do this side before we move on. The total current is 6, which means 3 plus 1 is 4, so the current here should be 2. Now, ranking of resistance. So let's think about this, okay? Remember our formula. Current equals, what is it, voltage over resistance, right? So, we know that this can change in a parallel. But let's look at something. In a parallel, the change in voltage, that's voltage from a battery, equals the drop in voltage or change in voltage of 1, which equals the change in voltage of 2, which equals the change in voltage in 3. All right, so what does this mean? Does this look familiar? This is kind of the same law as the series law for current. In other words, in series, the current is always the same throughout the whole thing. But the voltage will slowly drop, right? How we talked about that? Well, in parallel, the voltage is always the same. And it just, when it does drop, it drops all at once. In other words, it's 12 volts in, it drops all the 12 volts drop all at once, right? So the voltage never changes. So let's think about this, because we're talking about this so we can do these. if voltage is constant, let's say it's 12. So we have our current equals 12 over our resistance. We're trying to find the resistance, or at least rank them, right? So let's look at A, or let's look at, it's actually C. C, the current is 5 equals something over resistance. B, it's 4, and A, it's 3. So because our voltage is the same, doesn't that mean the higher amps you have, the lower the resistance you have, which is one of those laws we underlined. So again, remember, your current equals your voltage over your resistance. In a parallel, the voltage is constant, doesn't change. Or it drops all at once, so it's constant over the different circuit lines, right? So if your current in one of them is 5, for example C, that would mean that R would have to be smaller to increase this. Whereas if it's 4, R would have to be a little bit bigger than this one, right? Because it has to go in 4 times versus going in 5 times. Which means the higher the current, the lower the resistance. So what does that mean? That means that the least resistance was C because it has the highest current. And then the next least resistance is B and then A. And let's look at this one. The least resistance will be the one with the highest current, which is B, and then A, and then C. Okay. Don't worry if you're having a hard time with this, guys. I promise you, when I first looked at these units, some of the stuff I had no idea, and I had to just learn it. And, you know, I got it, and you can get it. I promise. Just take your time. Don't freak out. That's the biggest thing that, like, makes people not get this stuff is they freak out, and then they get nervous, and they can't learn, right? So just relax. You'll get it. No worries. All right. So a 3-resistor parallel circuit is created. The resistances of the resistors, okay? The resistances of the resistors are 3, 6, and 9. Okay? Suppose that one observes the current through the 3 resistor to be 6 amps. All right, so I'm going to write on this and cover that up because it's getting confusing. So they're saying, yo, they have 3 resistors, a 3, a 6, and a 9. Remember everything we talked about. Rewind it if you don't remember. They're saying, yo, they saw one. They observed the current through one of the resistors, one of the 3 resistors. Let's write a formula. Current equals voltage over resistance. One of the resistors, the 3 one, the current was 6. So with that being said, that logic, doesn't that mean that the voltage has to be 18? Right? Because we just did the formula. So with that being said, remember what we just said. The voltage in a parallel circuit equals the same, all the voltages equal the same all the way across. So the voltage drop across the 3 ohm resistor must be, well, what did we just say? That's what I said. 18. This provides sufficient evidence to conclude that the voltage drop across the 6 ohm resistor must be, well, the voltage is the same, so 18. We could do the math and prove it, but we don't have to. And the voltage drop across the 9 ohm resistor is 18. All right, so you get that? Hopefully you guys get that. So, therefore the current, which is I, in the 6 ohm resistor. Alright, so let's look at this. The 6 ohm resistor, so that means the resistance was 6. The voltage, again, is 18. The current in that one is, well, should be 3, right? Easy. And the current in the 9 ohm resistor, okay, well, let's do it. Current Is that showing up? Yes. Voltage is still 18. Resistance is 9. So that should be 2. Awesome. When these three branch currents combine, one would observe that the current in the blank volt battery, well, again, we just said that the voltage is always going to be 18 across, is how many amps? Okay, so we calculated that. All right, let me gather my thoughts. Hold up. I'm getting scrambled. All right, I gathered my thoughts. So, back to it. These are the three resistors, right? We calculated the 6 and we calculated the 9. Let's go ahead and finish off and calculate the 3. That's 3, right? So current and the other one is same voltage, 18, divided by the 3 ohm resistor. That's not 0.9, that's just a straight mark. 3, which means the current in the other one is 6, which means the total current, because remember what we said earlier, the total current equals add all the individual currents, right? So the total current would be 6, 7, 8, 9, 10, 11. 11. Oh yeah. So, in summary, the voltage, 18 all the way across. The current in the 3 resistor was 6. Oh, that's already given. The current in the 6 resistor was 3. And the current in the 9 resistor is 2. So now let's talk about the total, the current in the battery. The total current in the battery was, we said, was 11. The total voltage in the battery was 18. And the voltage of the battery minus the current of the battery. So that's 18, right, divided by 11, because it's total versus divided by total, is, should have got like 1.63. We'll just round that. There we go. So, hopefully you guys are getting this. It's not as long as the other video. That's a little shorter. All right, consider the circuit on the right. So we've moved on to a new circuit. There is a voltage drop of blank volts across each 2 ohm resistor. Remember, the total voltage drop, what we said, the voltage, they ride together, they die together, right? So the total voltage in a parallel circuit is always equal, and when it does drop, because it drops because it gets used, they drop together. So the total voltage is 6, which means they drop together 6. By Ohm's law, the current in each 2 ohm resistor is blank amps. Okay, so let's look at this. Current equals, the voltage is 6 divided by the resistance. Well, since they're both the same, so let's just pick this one, 2. So that should be 3. Right? Current equals 3. Awesome. The current through the battery is blank amps. So remember, this, let's label this. 1, let's call this A, B, right? So we just did the current for A. Let's do the current for B. Current equals, the voltage is the same because it's parallel, divided by the resistance, which happens to be the same, but we're doing B, right? So 6 divided by that's 3, which means the current through the battery is 6. The resistors in parallel offer a combined resistance of, okay, so this is the thing that we haven't talked about yet. Let's look at this page. Equivalent resistance in parallel. So our formula is 1 over the equivalent resistance, or the total resistance, equals 1 over the resistance of 1 plus, oh, you guys can't see, you'll see it in a second. I'm writing the same thing. 1 over the resistance of 2, so on and so forth, right? So we got to look at this one. Oh, we got to bring it up. There we go. So here's our deal. So we have a 2 ohm resistor and a 2 ohm resistor. So our equivalent resistance equals 1 over the first ohm, which is 2, plus 1 over the second resistor, which is 2. So that's 1/2 plus 1/2. We know that's 1 over 1. It's 2 over 2, which is 1, right? Your answer goes on the denominator, right? So it goes here, which means our resistance is, our final answer is 1, this 1, divided by what we just got, which is 1. Okay? No, it's a little tricky. 1. You dig it? Good. We did it. Yeah, I did it. Okay, is this the last page? It is not the last page, but it is the second to last page. So that's good. So, alright, oh, it's wearing me out. Alright, determine the equivalent resistance of the circuit at the right. Okay, so remember our formula, which is right here. 1 over the resistance of this, plus 1 over this, plus 1 over this. So what we're going to do is 1 over 5 plus 1 over 4 plus 1 over 7 equals 1 over our equivalent resistance. So in other words, when we add these together, it goes on the denominator, and then we do 1 divided by what we got. So what you should get, if you don't get this, it's because you didn't divide what you got into 1. That is the reason why you didn't get what I'm about to write. You should get 1.69 ohms. If you did not get this, it's because you got a bigger answer most likely, and you just wrote that down instead of doing 1 divided by whatever you got. Okay, so that's the only reason you would have not gotten this. All right, let's look at number 10. Determine the overall current in the circuits as determined by at position A or H. So it wouldn't matter because, you know, overall current. Okay, so we're using our formula. Current equals voltage divided by resistance. Our voltage doesn't change. What's our voltage? Doesn't change, doesn't matter. 30. So current equals 30 divided by our total resistance, which is what we just calculated, 1.69, because we're trying to find the overall current, the total, which means our overall current would be 17.75 amps. Good. Stay with me. We good? Don't yawn. That means you're not paying attention. Your brain's taking vacation. Keep going. Here we go. 11. Determine the electric potential difference, voltage drop, across the 5 ohm resistor B to C. Remember, we wrote this somewhere. Where do we write this? Way back over here. In a parallel, the voltage drops equally over all of them. So the voltage pretty much stays the same, and it drops all together. Which means, there we go, move that sucker over. For 11, the voltage drop will be 30. Determine the current through the 5 ohm resistor. Okay. Current equals voltage divided by resistance.
Hi, Daddy.
Hi. Current equals 30 divided by this resistor, which is 5. So the current will equal 6. Alright, so let's do number 13. Determine the current through the 7 ohm resistor. Current equals voltage over resistance. Voltage is going to be the same, 30. Current we're finding, resistance is 7. 30 divided by 7 equals 4.3 amps. There you go. So let's do number 14. We're doing good. We're on a roll. If resistors are connected in parallel, then electric potential difference or voltage drop will be greatest, okay, that means there's going to be a difference, across the resistor with the greatest resistance. We just said that they're all in. They're all the same and they drop all at once in a parallel, which makes this false. Ride or die in parallel circuits. 14. If resistors are connected in parallel, then the current will be the same through each resistor. So if resistors are connected in parallel, then the current will be the same through each resistor. Again, we said this earlier. The current can be different in a parallel with each one depending on the resistance. It's not the same. In a series, the current's the same. In a parallel, it is not the same, as we just kept doing, right? So this is also false. You are a false god. Question. Number 15. A 2 ohm and a 4 ohm resistor are connected in a parallel circuit. The electric potential difference, i.e. voltage drop, across the 4 ohm resistor will be blank the electric potential difference across the 2 ohm resistor. Well, here we go. It's on repeat. The voltage drop will be all the same across all of them. It's all the way up or all the way down. When they drop together, and they're up together. So the same as. Alright, number 16. A 2 ohm resistor and a 4 ohm resistor are connected in a parallel circuit. The current through the 4 ohm resistor will be blank the current through the 2 ohm resistor. Well, let's think about this. They're connected in a parallel circuit. So we have current equals our voltage. We're just going to put a number sign over 2. Current equals our voltage, which we're going to put a number sign over 4. Which one do you think is going to have the greater current? Remember, current is I. It's going to be the one with the least resistance, right? Because the smaller this bottom number is, the more it'll go into this top number. Therefore, the current through the 4 ohm resistor will be 2 times less than this one. Because if you double this number is going to be half. Think about that one for a second. It'll set in. Alright. Almost done. Dang, we're already at 27 minutes. The heat's turning up. I think you got 5 days for this one anyways. Okay, so we're going to 17. We did one exactly the same as this one, but let's do it anyways. So let's write our formula. The equivalent resistance equals 1 over the resistor for 1 plus 1 over the resistor for 2, so on and so forth. So this is 1 over 2 plus 1 over 2 equals 1 over the equivalent, which means this plus this is 1, which means it's this 1 over 1. 1. Easy. Let's do this one. 1 over 4 plus 1 over 4 equals 1 over the equivalent. That equals 2 over 4, which equals 1/2. 1 over the equivalent equals 1/2. That's 0.5, right? This will make it a whole lot easier if you change that to 0.5. 1 over 0.5. How many times does 0.5 go into 1? 2. Bam! Look how easy that is. We're so smart. Let's do this one. 1 over 6 plus 1 over 6 equals 1 over the equivalent. That's 2 over 6, which equals 2/3, equals 1 over the equivalent. You could change that to like 0.666 or whatever. We're just going to round it though. So 1 divided by 2/3 or 1 divided by 0.66. And that averages out to about 3. Okay, so you get the hang of these. I'm going to do one more easy one, and then I'm going to do one of these ones at the bottom that are not easy. Let's do this one, the 8 one. 1 over 8 plus 1 over 8 plus 1 over 8 equals 3/8. which equals 1 over the equivalent. So 1 divided by 3/8. You can change this to a decimal if you want. You should get about 2.6 repeating. All right, let's look at these. Let's do the big one, 16, even though they're going to be similar. 1/16 plus 1 over 1 plus 1 over 1. So this is going to be times 16. So it's going to be 16 over 1. We're going to change this to 16 over 1 because that's still 1, right? Still 1 over 1. Which means we're looking at 32, 33 over 16 equals 1 over the equivalent. So 1 divided by this, you should get a very small number of 0.48. Okay? Cool. So I'm not going to do the rest of those. Hopefully you guys get the hang of it by now. Let's finish it. Is this the last part of this page? Yeah. 18. This is it. It's the final stretch. 4 resistors are connected in a parallel circuit. 3 of the resistors' values are known. 3, 4, and 6. The overall or equivalent resistance of the 4 resistors must be blank ohms. Choose the answer that is most informative. So there's 4 resistors. 3 of them is 3, 1, and 6. So we have 1 over 3 plus 1 over 4 plus 1 over 6 plus 1 over question mark equals 1 over the equivalent resistance. So let's just do these for now. 1/3 plus 1/4 plus 1/6. I think that let's change these to things that will actually have like terms. So this would 8 over 24 times 8. This is 6 over 24, and this is 4 over 24. So now we have 16 over 24. Can we reduce that? Is 2 over 3 equals 1 over the equivalent. Hopefully everybody's with me. We're forgetting about this one for now. We're just going to see what we get if we don't have it. And I think we did something like this. 2 over 3. So, no, that would mean our equivalent would be, okay, the overall resistance. So our overall resistance is 3. So that tells me already what we actually already found the answer. I didn't know it was going to work out this way, but our overall resistance, according to this one, because it was 2/3, right? And this ended up being 2/3 without this. So our overall resistance would have to be equivalent to this if you didn't have this. So if you added this in, did I do it right? No, I think I did it wrong. Let's see. Choose one. Let's see. So remember, if we increase the resistance, then we decrease the current, right? So in this case, it is going to be D. And that's it. We're done. We're done-ski. It was a long one, but we did it. Good job, guys. If you got questions, ask me. That's it. Good job, guys.